Okay, good afternoon, everybody. My name is Tim Chan, and welcome to the latest edition of the MI webinar series. Today, we'll be focusing on feedstock acquisition for biomethanol production. This is the lineup of speakers that we have today. Unfortunately, David Chung from Enerkem will not be joining us because he's based in Canada, but he has already sent us a video recording with his presentation slides and also a bit of a description of what Enerkem is doing. So we'll still be able to hear from David. Unfortunately, we'll just not be able to give him any questions about the content that he's presenting today. But don't worry about it. We will be able to connect him if you do have any questions after this webinar. So without further ado, I'll begin today's session. Once again, my name is Tim Chan. I'm based in Singapore, and at the Methanol Institute, I cover the Asian and Middle Eastern markets. And the Methanol Institute is the global trade association for the methanol industry. It was founded in 1989, founded in Washington, D.C., but we moved our headquarters to Singapore. And since 1989, we've basically started different offices around the world, and you can see on the map, we have an office in Brussels, an office in Delhi, as well as one in Beijing. Once again, I'm based in the Singapore office. So if you do have any methanol questions, whichever part of the world you are, you would likely be able to meet with or at least get in touch with some of my colleagues in the different offices that we have around the world. So this is the membership structure of the Methanol Institute. To give you a short introduction, it's a tiered membership. The first tier includes most of the major methanol producers around the world. Tier 2 is slightly smaller. Tier 3, you see some technology companies as well as methanol distributors. Tier 4 is where it gets really interesting in the last couple of years with the whole issue of energy transition and decarbonization. Interest in methanol as a fuel, as a green chemical, has been growing quite rapidly. And many of the companies you see in Tier 4 are companies that were not traditionally from the methanol business. They might be in shipping. They might have an interest in utilizing methanol as a green ship fuel. There are companies that are developing fuel cells and methanol reformers to produce hydrogen for refueling or power generation. And we also have companies that are producing or aiming to produce e-methanol or biomethanol, which is the focus of today's webinar. So to give you a short introduction before I introduce my speakers, as I mentioned earlier, the interest in methanol as a product, mainly as a fuel and chemical, has been growing. Has been increasing in the last couple of years due to the pressures of decarbonization and lowering our greenhouse gas intensities of different industries. And methanol is conventionally produced with natural gas. Some plants around the world do use coal, but by far and large, most conventional plants produce methanol utilizing natural gas. But the interest in methanol these days extends from our main current mode of production, which is the utilization of natural gas, to the utilization of more sustainable feedstocks, such as biomass, such as renewable electricity, municipal solid waste, biogas. Some of the speakers today will be introducing some of the feedstocks that they deal with, and we're going to find out how they sit on these new value chains where sustainable methanol will be produced as a green fuel and a green chemical. To give you some background, the Methanol Institute collaborated with IRENA in 2019 to develop a study that would look at future green methanol markets. We looked at how green methanol can be produced, what the future projected demand can look like, and according to IRENA, they projected by 2050, 250 million metric tons of e-methanol will be produced and 135 million metric tons of biomethanol will be produced on an annual basis. And these projections are far from where it is. The state of the global industry right now is our global production capacity is 140 million metric tons. So from IRENA's perspective, they really see a huge period of growth for the methanol industry over the next coming years because of other industries looking to utilize green chemicals and green fuels. And one of the reasons why methanol is gaining traction as a sustainable fuel is because of its physical properties, its inherent physical properties, where it is a liquid at ambient temperature and pressure. So this actually helps with the handling and utilization of methanol, which is not very unlike conventional fuels that we're quite familiar with today. But as the industry explores the production of methanol from sustainable feedstocks, there is a recognized, or at least it's acknowledged among the industry, the methanol industry, as well as our clients and our other different stakeholders, that methanol, with its ease of handling and utilization, could play a significant role in decarbonizing many different other sectors, such as transport, such as power generation, and even the utilization of methanol as a hydrogen carrier for future hydrogen energy landscapes. So the focus of today would be on biomass or bio-related feedstocks in the production of methanol. So that will be the top level of the graph that you see on the left-hand side of your screen. So one of the challenges that we're trying to address with today's session is the acquisition or getting access to sufficient quantities of sustainable feedstock for biomethanol production. So there are some challenges with producing bio and e-methanol. I think that is widely acknowledged by the industry, and in our process and in our efforts to scale up sustainable production, one of the key challenges that we need to address is how do we get access to critical amounts of feedstock that will warrant investments in new plants that will utilize sustainable feedstocks for biomethanol production. So that's just setting the context for today. One more thing to add, on the Methanol Institute website, if you go to it, you would find this sort of global map where we track different projects around the world. It's an interactive map, so you can basically move your cursor over some of these icons to show you, and it will reveal the name of the project, the projected production capacity, and the startup year of these different plants. So if you want more access to E and biomethanol projects around the world, the MI website is a good place to go to. Alternatively, you can reach out to any of the MI staff in our different offices around the world. So with that, I think I'm going to pass the time on to my first speaker, Carlo from Studio Gear Up. He's going to be speaking about CO2 for e-methanol production from an LCA perspective. Carlo, I'll pass the time over to you. Let me pass you some control so that you're able to control the slide deck.
Thank you, Tim. Good morning or good afternoon to all, wherever you are. Thank you for having me today. Indeed, I'm going to tell you about the use of CO2 for e-methanol from an LCA perspective. And also, it's quite focused also on the European legislative perspective, which has some ideas on it, but which I think are consistent also with the LCA perspective. But sometimes it's easier to explain it from the legislative perspective. 2 years ago, we've done a study for MI, well, between 2 and 1 year ago, and it's published. You can find it on the MI website, about the carbon footprint for a wide range of methanol pathways, ranging from natural gas to biomass and e-fuels. The idea with renewable methanol in the first place is that the CO2 that is emitted at the end has actually been absorbed from the atmosphere rather shortly before. And so you have a short CO2 cycle, and with the combustion at the end of such a methanol as a fuel, you actually have no net emission to the atmosphere of CO2. So that's the big idea, and I hope that all of you understand this by now, and otherwise I really would advise you to read that report. Today I'll be zooming in on e-methanol in particular. So e-methanol is methanol produced from renewable hydrogen plus CO2 and over a catalyst to produce a methanol. And the E then stands for electric. So it's a renewable electricity-based methanol. You will find also more details in that report that I mentioned. The link to the report is, by the way, also at the end, but you find it also on the MI website. But without further ado, let me go to the next slide. If that works, yes, very good. There is a slight delay, so I have to be patient. I'm just recapping one slide from that study, and that's the slide on e-methanol. Assuming that the CO2 that is being used in the e-methanol has no climate impact, you don't see the end-of-life emissions in this graph. So in other graphs in the report, you would find a big gray bar on top of these bars, and that's, let's say, the typical end-use emission. It's stoichiometric, 69 grams per megajoule, or something about 1.4, I think, tons of CO2 per ton of methanol that you would just emit in terms of CO2. But we don't show it because it has, in this case, been captured from the air in one way or another before. I'll come to the details of that later. First, you see here that the performance of e-methanol can be quite different. If we produce it from solar energy, from wind or hydroelectric sources, so from renewable sources, then actually you have very little supply chain emissions. But if you would take an average grid electricity, it is not renewable anymore, and then in the production of that electricity, more CO2 is emitted, and you would actually have a quite high emission profile. And the emission profile of the EU would bring it at around 100 grams per megajoule. By the way, I see that the legend of the graph is not entirely correct. It should read per megajoule. And it's so this actually would just put it at par with fossil-based methanol, which is also around 100 grams per megajoule. So we really need to focus on renewable electricity, otherwise it doesn't make sense. Details, again, you can find them all in that report. So, but there is something with the source of the CO2 that I want to draw your attention to. First of all, e-methanol in Europe, we call it an RFMBO, a renewable fuel of non-biological origin, and it is also stimulated in that sense by the Renewable Energy Directive, the current one, and also the upcoming one. Actually, the upcoming Renewable Energy Directive, the one that is has been discussed in Parliament and that will be discussed in the trilogue, so soon will be also hopefully legislation, asks for 2.6% of all energy in transport to concern RFMBOs. The Parliament and actually also the Commission even would like to go higher with that, and it would go to maybe a 5.6%. And also in aviation, there's actually also a sub-target on volume basis that 0.7% of all the jet fuels should consist of RFMBOs. So this means that there will be a significant demand for RFMBOs. It's almost, let's say, guaranteed by legislation, and e-methanol is an option. The source of all the RFMBOs is obviously renewable hydrogen, and that has to be based on renewable electricity. So could also be that a large part of the RFMBOs is renewable hydrogen, and obviously there's also other options like I mentioned E-jet, Fischer-Tropsch pathways. Several more pathways are possible, but we think that there could be a quite interesting market for e-methanol. There are some restrictions, and that has to do with, on the one hand, the additionality requirements for the electricity. So the Commission proposed to have very strict requirements for the time and the geography of where the electricity is being sourced from. So really to prove that it is based on an additional amount of renewable energy. Now this has been scrapped by the European Parliament, and so it's not a rule on a European-wide basis. It could still be a rule on some national basis. It's very difficult, and I don't have the time to go into the details of this additionality requirement here, as I'm focusing on actually the points 2, 3, and 4 that you also find at the bottom of the slide. The thing is that if you produce from combining CO2 and hydrogen, you can any CO2 emission reduction that occurs along the supply chain can only be credited once. And another one that is important is that if you would use a fossil-based CO2, then this is can only be done until 2035. So after that, you would have to have access to another solution. If the CO2 would be sourced from an ETS obliged facility, then the emissions are assumed to take place still in that facility, and it would require the seller to buy emission allowances for it. And this is quite critical, I imagine, and therefore I've worked it out in a next slide in which we can see it rather a bit more schematically. So here, this is, let's say, options for fossil-based CO2 from industry. And at the top, you see, let's say, the current situation. We have an industry, could be a power station, could be in an ethylene oxide facility, anything that produces CO2, and some produce it at a higher concentration. If you have in Europe, if you have a industry that produces a significant amount of CO2, you get an obligation in the emission trading system. And it means that for each ton that you emit, you need a permit, an allowance. And this is costly. It's at the moment €65 per ton CO2. And as the ceiling of the emissions go down, these allowances are auctioned. So each year less allowances come available. Each year the price could go up. So this can become quite a costly business over time. Industry will do their best to reduce their emissions. One way that they could do is that they would apply CCS, carbon capture and storage, and then the emission does not take place, so they don't need to buy an allowance for this emission. And from an LCA perspective, we can say there is an emission reduction because we don't have an emission compared to the status quo. If now, and that you see at the bottom, we use that CO2 from the capturing, so we capture it at the chimney and we bring it to a second factory where we combine it with renewable hydrogen, then we produce an e-methanol, and then we use this e-methanol, let's say, in a ship as an e-fuel, and the ship emits CO2 because it combusted. So there is a stoichiometric emission of CO2. This means that if you look at the scheme, sooner or later, the CO2 emission is still released to the atmosphere. And it is still also a fossil-based CO2. So in this setup, there is a net emission to the atmosphere. There is not an emission reduction anymore. Somebody will have to pay for this emission. So either it is at the source, at the seller, let's say the power station. They may still have to buy allowances. If they buy allowances for the CO2, then basically the CO2 becomes climate neutral, and then the e-methanol also becomes a renewable e-methanol in the sense of the RFNBOs in Europe. But also from an LCA perspective, I think it makes it quite clear what is happening here. So somebody needs to put the CO2 emissions on their balance. If the power station does not want to buy the allowances and they say we have saved emissions, then basically the CO2 is not climate neutral and would have to be counted at the end point in the e-methanol. And that would put actually some 69 grams on top of the graph that I showed before, which would make it rather unattractive even for renewable-based e-methanol if it would be sourcing such form of fossil CO2. So this is, I tried to explain it in the most clear way, but I know it's cryptical. You may have to think about it. Please do so, and I'll hear your questions in the panel. In the meantime, I'll try to also show you another option, and that's if you would use bio-based CO2 from industry. Now, the idea with biomass use, let's say in a biomass power station, is the CO2 goes to the atmosphere, but is also absorbed by the biomass in the first place. So this is a net zero option at the top. If you would apply something like CCS, then actually this facility becomes carbon negative. It becomes like a vacuum cleaner for the atmosphere, and we suck up the CO2 via the biomass and we put it in the subsurface. That such solutions may be necessary as other sectors of the economy are overshooting their CO2 emissions. At the bottom, you see what happens if we use that same CO2 captured at the chimney, producing an e-methanol in the ship. So it's almost the same setup as in the previous slide, but now it's from biomass. Then still, you could say, in this case, it can happen that the CO2 that is emitted at the end is still a biogenic CO2. So it counts as zero. So both the biomass power station are zero emission and the ship is zero emission, or the e-methanol is zero emission. So this is a very attractive situation. If, however, for some reason, the biomass power station would like to claim the emission reduction that they have achieved and they would like to go to net negative, then it's not possible anymore. So you can, let's say, count the CO2 two times, one in avoiding a fossil emission, and the second time because it's because it does not add to the atmosphere in a way, but you cannot count it three times. So you could not say, I'm not emitting it, I'm storing it somewhere, and I'm also not emitting it in the second place. So you have to make a choice here. One variation that we can make is, and it's quite an interesting one, on the last slide with the schemes here. That is, if we don't have a power station, but we have, oops, I did not want to jump to the conclusions yet. If we have not a power station, but we have a biofuel production facility, a production facility that also emits CO2. Let's assume it's either a ethanol, in the production of ethanol, the co-production of CO2 is almost a kilogram per kilogram, or in a biogas installation, also significant amount of CO2 in a rather pure form is being produced. The CO2 would normally go to air when the biofuel is consumed in the vehicle. Also, there's a CO2 emission. And actually, if you add up all the CO2 emissions along the supply chain, it's the same as what has been absorbed by the biomass in the first place. So this is perfect, and it is carbon neutral. It's net zero. If we, again, we follow the same pattern, we would apply a CCS there, then actually the biofuel you could say is, with this supply chain, removing CO2 from the air. So we're not only saving fossil carbon emissions by putting the biofuel in the car, but the whole supply chain is even removing CO2 from the atmosphere. In the European legislation, this is awarded by kind of a credit, a CCS credit. Now, if you would not apply CCS, carbon capture and storage, but carbon capture and utilization, CCU, you could also get this credit, but not if we, and that's at the bottom, if you would, again, use it in the production of an e-methanol and then use the e-methanol in a ship. So now we see, hey, there is a CO2 emission. There is, of course, also, I should have actually also made another arrow back to the biomass. So the CO2 at the end is also, in essence, neutral, that you see. There is no net CO2 emission. But this advantage can, again, only be claimed one time. It's either the e-methanol is neutral and doesn't have the CO2 emissions, and also, of course, the biofuel that has been produced does not have the CO2 emissions, but you cannot say that the biofuel is carbon negative at the same time. And this could be not so attractive for some of the bioethanol producers, because bioethanol producers also want to improve the CO2 emission performance. So if they have a good access to, if they could capture the CO2, and if they could sell it, for example, to greenhouses, they would like to use this credit, but then it would make, then the CO2 that is subsequently sold to the e-methanol producer would not be climate neutral anymore. So again, it's one or the other, and you cannot have, you cannot take the advantage multiple times. I imagine this has been complex. I hope that if there is some questions, I can further clarify, but I also hope that the schemes have made it a bit easier to understand what happens. Let me then come to the conclusions. So first of all, I don't want to end with a negative note, but you just need to be careful. There will be a huge demand for RFMEOs in the EU, and I suppose also elsewhere around the globe. And it could also really imply an interesting market for e-methanol. It does depend on the source of the CO2 and also on the alternative options that the CO2 seller has. In any case, the use of fossil CO2 will be limited in time, so you will have to make sure that if you would build your business case on this, you also have another option to jump over to. E-methanol is only interesting if the CO2 that is emitted from the end use can be regarded as climate neutral. Otherwise, the minimum required greenhouse gas saving will never be achieved. So CO2 emission reduction can be achieved via carbon capture and can only be claimed once. So it's either at the seller's location or at the e-methanol location. And whether this is interesting for the seller, I think, will depend on the value of the climate-free CO2 molecule. The options for the seller, will he have access to storage? Is storage an alternative? The price of CO2 emission allowances in case of fossil-based CO2. And also, what is the value of an improved greenhouse gas performance for the biofuels, for example, for ethanol, if they would apply CCU? So there's multiple factors that would have to be considered. We didn't dive into this yet, but this is, I think, an interesting maybe food for thought. With that, I hope that I have shed some light and not added too much confusion. And I look forward to the questions.
Thank you, Carlo. I think at this point in time, before we move on to the next presentation, to just provide some context to participants as to why we invited Carlo to speak, mainly because of what is going on with the RED2 delegated acts on RFMBOs right now, and there's a lot of debate and discussion on whether it's industrial or whether it should be biogenic, and of course this will affect some of the existing projects that are being developed, but also future projects that are in the pipeline. But at this point, Carlo, I think maybe I could ask you maybe one or two questions about some of the content that you have presented. I think we had this conversation a while back also. From an LCA perspective, or maybe just to set the context, the choice that was made at the EU to prevent the use of industrial CO2 beyond the year of 2035 in the production of sustainable fuels was a policy position that the EU took to prevent the further utilization of fossil fuels and industries that emit or that they are emission intensive. But from an LCA perspective, do you think that there is an argument for industrial CO2 to continue to be used? Mainly because if we use industrial CO2 to produce not only e-methanol, but other fuel types that require the carbon source, it also displaces the requirements for fossil fuels in downstream markets, like say, for example, the maritime industry. What are your thoughts or position on that?
Yeah, I think that at the moment it would not be necessary per se to restrict the use of fossil-based, or let's say the use of industrial CO2 per se. If the other rules are applied, this would become less and less attractive anyway. And what we will hopefully see is that that same industry is also more and more based on renewable feedstocks, and they will have their own drivers. And so eventually it could be the case that fossil is gradually replaced with renewable biomass feedstocks in industry, and those emissions automatically become biogenic and therefore climate neutral, and you would have a kind of a circular system there with the CO2. So I can see the point of the Commission. They always want to push from different sides on the same topic, but it would not be necessary. I think it's demotivating maybe a bit for the industry because if there is a phase out of this, well, if there is a hard stop to this in 2035, and you still are now planning to build your factory, then it's maybe coming online in 2025, and then you have just a business case of 10 years, which is, I suppose, too short for many business cases. So it seems that this doesn't really make sense. Rather, you would like to give more perspective to the industry and tell them how they can step over from that moment or in the course of time.
Right. Thanks, Carlo. Maybe just one quick question before we move on. When we talk about RFNBO, it is only one category of future sustainable fuels that the EU is looking at here. So I think there is conversation going around that that there is a framework or provisions are being drawn up for recycled carbon fuels. Would that be a separate category altogether, and how does it stack up to the likes of, say, for example, RFNBOs?
Oh yes, recycled carbon fuels are definitely another category. I think the enthusiasm, the political enthusiasm for recycled carbon fuels is much less. But also there, maybe at some point in the future, they would rather flow together in a way, because the carbon in the recycled carbon becomes more and more renewable, I hope. But for the moment, there is, on the one hand, there is a lot of industrial CO2 there, and a lot of that is fossil-based. And if you can give it a second life by carrying hydrogen and then in the form of methanol, I think that's a perfect solution. And whether it is via an RCF that this fossil carbon finds another use, or via an RFNBO, both would be good. And at the same time, you would also need to understand, okay, what is necessary in 10, 15 years from now, from your business perspective, but also from the climate perspective. The aim should be that the net climate emissions are being reduced. So yeah, we should rather see a closing of the fossil tap.
Thanks, Carlo. Yeah, I think those were the questions that would set the stage for the presentations that are to come next, where they will talk about the different feedstocks that they acquire biogenic or sustainable carbon from, but also, I mean, in the widest context, where there's the ongoing conversation that that biogenic sources might be hard to get access to, and industrial seems to be a bit more immediate. But definitely, it seems like from a policy perspective, and also from a business perspective of some companies, that it's about this sort of transition from fossil to biogenic, and maybe, I mean, in the context of biomethanol, I mean, or e-methanol, it could be even direct air capture in the future.
Yeah.
So thanks, Carlo. Well, oh, sorry, did you want to say something?
No, I didn't mention direct air capture, but obviously that's being seen as the source of CO2 towards the further future. But thanks for adding that.
Thanks, Carlo. I'm sure we will have quite a number of questions for you during the Q&A, but for now, we'll pass the time on to ABEL Energy. With ABEL Energy, we've got Michael here who'll be talking about their project that they're developing in Australia. Michael, let me pass you controls, and you should be able to begin your presentation right now.
Thank you, Tim. Yes, I'm grateful to the Methanol Institute for inviting us to speak. We are speaking, of course, on the basis of a project that we are developing in the southern Australian state of Tasmania. And the reason that we were drawn to Tasmania was a number of reasons. Firstly, Tasmania is the only state in Australia which has virtually a 100% renewable energy grid. So most of the electricity generated in Tasmania is via hydro, but it also has an excellent wind resource. So we have a situation in Tasmania where there are no fossil fuel power plants, there are no gas or coal-fired power plants currently in operation. There is an interconnector, but essentially you can almost assume a near 100% renewable power grid. And of course, if you're making hydrogen for the methanol, that's very important. The other thing that Tasmania has is a very good forestry industry. And when you combine the forestry with the renewable power, with the fact that we're on a seaport at the port of Bell Bay, you can start to understand the attraction for us in developing our first project in northern Tasmania in a port called Bell Bay. So for the last 18 months, we have been involved in developing a feasibility study for the project. You can see some of the participants there: ThyssenKrupp, PwC, Pitt and Sherry. And we studied a model which looked at essentially a hybrid of e-methanol and biomethanol. So we had 100 megawatts of electrolysis being studied to produce hydrogen, but we also drew on local biomass from the forestry industry to generate sufficient volume of carbon dioxide through oxy-fuel combustion of the biomass. The output for that study was 75,000 tonnes of green methanol. So it was a significant project. But in the process, we learned quite a few things. Firstly, we realized in the course of the study that moving to a larger scale, if possible, would give us a significantly lower cost of production. Secondly, we noticed that if we could move from 100% CO2 as our carbon source to the use of carbon monoxide as well as carbon dioxide, that we again would increase the efficiency of the process and reduce the volume of hydrogen that needed for the production of the same quantity of methanol. So, but of course, in all this, we have to try to make sure that we're producing something that, you know, that does genuinely reduce the carbon intensity of the product we're making, and that we are able to align our views and interests with those of our customers, which will be people like the shipping industry, people like the mining and chemical industry who want to go green. So, and of course, as Carlo mentioned, you can't just build on a 10-year project. You have to build based on a 25-year plus project timeline. So, and it's quite difficult when you have various countries around the world all looking at different schemes and different approaches to the carbon intensity of your feedstocks. So in the end, we decided that the best thing we could do was to set out some guiding principles for ourselves, and then make sure that those principles align with our customers, which from a volume point of view, the first movers are clearly the shipping industry. And secondly, that we give ourselves the best chance that when the rules are settled, whether they're in Europe or North America or in Australia or Japan, that we have followed some principles, first principles that give us the best shot of complying with those rules. And of course, the rules that are made in 2022 can be changed in 2024, in 2026, 2030, and again for a 25-year project. This introduced risk, and again, the best way to manage the principles. So the first principle we decided was not to worry about using industrial sources of CO2, at least none that didn't come from the biosphere. So the only carbon we're proposing to use is carbon that we can obtain from the biosphere. And we also felt that it was important to acknowledge right from the beginning that the only way that methanol can be scaled up to the volumes that are anticipated, industries like the shipping industry, in theory, if they would replace heavy fuel oil with methanol, would need, in today's terms, about 700 million tons of methanol. And there is only 100 a day, and that's mainly made from gas and coal. So the sheer scale required is that we think direct air capture is the way that we would need eventually to source our CO2. And to that extent, we strive to be an early adopter. So we are going to have a demonstration plant at the Bell Bay project, which will demonstrate the capture of CO2. In my mind, once the energy consumption of capturing a ton of CO2 falls below 1 megawatt hour of electricity or heat, then you've got a really interesting proposition, because then really most of your energy is going to be needed for the hydrogen, not for the carbon. You might need 8 to 10 hours of energy, of electricity, to generate your hydrogen. And if you only need 1 or 1.5 megawatt hours to generate your carbon dioxide for the 1.5 tons that you need for a ton of methanol, I think this is where the world will go. Of course, as I say, as a company that wants to develop early projects, this direct air capture is not yet available in the scale that's needed. So we need to rely on biomass, and in doing so, we don't want to contribute to deforestation or clearing of natural vegetation. If we stay away from that, we think we're on a good track. And to that extent, we need to work closely with the forestry industry in Tasmania and around Australia to make sure that there's a mutual benefit. The forestry industry is very important to the state of Tasmania. It provides a lot of work for people. It provides very high quality timber products, and as well as for the production of paper. So making sure that we all strive to achieve the best outcome for everyone concerned is very important. So just a little bit about, you can see there in the North Tasmania where our project is at the Port of Bell Bay. As I mentioned earlier, the use of biomass not only gives us an opportunity to make green methanol, within a time frame around the 2025-26 is when we're looking to start production, but it also gives us a very efficient source of carbon in the form of carbon monoxide as well as carbon dioxide. We it's sensible for us, and certainly our customers, I think, will demand that we only deal with plantations. There are a number of different certification schemes, but we think we can ensure that we stay within those schemes that have the most integrity. We want to use the lowest value biomass first. We do not want to be using bio oils, or as the renewable diesel industry has to contend with. And having said that, of course, there are other ways of using biomass which are starting to gather steam. Wood pellet production has not been a big industry in Australia, but we are starting to see the wood pellet industry also potentially competing for the same material. So that's something we need to be aware of. And of course, we don't want to be moving biomass large distances. We want to ensure, as we have tried to do, that we site our project in the centre of an industry where biomass is moved relatively short distances, and therefore that reduces the carbon intensity of our production process. So look forward to any questions, and thank you very much for your attention.
Thanks, Michael. Michael, thanks for introducing the ABEL Energy project. I think one of the questions that I have for you, and we'll entertain more during the Q&A session, but what was the biggest challenge in working with the timber industry in acquiring feedstock? And were there any solutions that ABEL came up with to circumvent some of these challenges or address them?
Yeah, sure. One of the biggest challenges, strangely enough, was the fact that, when you're moving biomass, the easiest way of moving biomass is via logs. So, but if you're looking to use forest residue, nice handy form. So we've been working with the industry to ensure that we adopt processes that are probably more familiar in Europe, where you're looking to use the residues from the harvest. That means new equipment, means a new way of harvesting. It might mean drawing a different line between material that is typically wood chip and what material is more sub-specification that we can best draw on. And in that way, we may increase the value of the wood chip product by moving it to a higher spec and taking that, giving the timber that lower spec material. So it's setting up a new process for taking forest residues which have traditionally not been taken. They've simply been left either on the forest floor or moved into windrows. That's our biggest challenge, Tim.
Thanks, Michael. And I guess in some agricultural sectors, they have different kinds of certification about the fact that the biomass was grown in a sustainable manner. Are some of these things also taken into consideration when ABEL sources for forestry residues?
Yes, it's very important, because even today there is still some remnant native timber or native forestry harvesting, which is quite controversial in some political circles, although it's not a simple story, but to some extent we avoid that sort of controversy by sticking with certification schemes and materials that have been certified in a way that our customers will be happy, and we have a long-term future without having to take on battles around material. And of course, we do not want to see clearing of native vegetation for our material. We think that's a bad trend. We think we should be looking to use as little additional land as possible for our materials.
Thanks, Michael. I'm gonna move on right now so that we can keep track. But we'll come back to you during Q&A. What I'll do right now is going to pass on the time to Kunal from Anaergia, who's going to be talking about their production of biogas as well as biogenic CO2 for the production of e-methanol. And they have a project that was announced quite recently in the news. I believe Kunal can share more information about that. So I'm going to pass the time to Kunal. There you go. You should be able to control the screen right now. And
fantastic. Thank you, Tim. Good evening, ladies and gentlemen here. Still an afternoon, evening to Michael there. I'm Kunal, Chief Growth Officer of Anaergia, and I'm going to talk about how we amass actually feasible feedstocks for biomethanol production. So let's talk a little bit about the problem. I want to take a step back before we leapfrog 2 steps forward. There are a few multiple problems. I'm not going to talk about general stuff like climate change. We all are aware about that. But this molecule, which is methane molecule, is really a massive culprit. And I mean, CO2 molecule has got all the limelight. But I think CH4 molecule, given any point of time, is 20 to 80 times more lethal than CO2 molecule. So one problem is the methane emissions in the world, and majority of the methane emissions come from organic waste sources. The second problem is a lot of waste out there. Human population has 3 times increased since 1950. We are touching 7.5 billion people. We're going to go a bit more. A lot of waste being generated. I'm talking about waste generated with human beings, industrialization, urbanization, etc. Look at this. If we were to combine food waste of the entire planet Earth as a country, it will be the 3rd largest greenhouse gas emitting country in the world. So after China and US. So the amount of greenhouse methane emissions which happens with food waste is just mind-boggling. This is another problem which I think in many developing nations you will see that thousands of hectares every year and millions of tons of agricultural waste is actually literally sadly burned, leading to, of course, greenhouse gas emissions, carbon dioxide emissions. But this is a massive problem. Come Southeast Asia, India, a lot of places, this is just burned. So this is another big problem. Now, let's talk about what can things be done. So imagine this garbage which you see in front of your screen, as well as the straw or agricultural waste, can actually power ships and maritime industrial decarbonization. Quickly about Anaergia, we are one of the world's largest organic waste to renewable fuel technology solutions provider. We are listed on the Toronto Stock Exchange, so probably Canadian company. We do only one business, and that business is to convert any and every kind of organic waste to renewable power, renewable gas, renewable fuel, recyclables, clean water, and fertilizer. We do not offer any equipment or technology. What we offer is waste particle coming in and a green molecule going out. So the entire end-to-end solutions. We also invest into projects. We partner with investors. We co-develop projects. We build those projects. We commission them, and we own, operate, and maintain them. So the entire life cycle partner, so as to speak. So generally, this is also a very key differentiator, because generally people will want to be the best technology provider and leave it there, leave it in the hands of developers, or developers are then on the mercy of investors. But we said, in order to move things forward and really move the needle on climate change, we got to walk the talk ourselves. So we develop, invest, and have our own technologies, and we sometimes partner with the third-party technology providers as well. Again, this is a similar slide. So look at municipal solid waste, wastewater, agri-food, and I'm going to touch upon a few more feedstocks which we look at while converting them into green fuels. We have about 231 active and pending patents in this space. The middle block, which you will see, is the proprietary technology piece across. So pre-treatment, anaerobic digestion to produce biogas, biogas upgrading to biomethane, CO2 liquefaction, wastewater treatment, and fertilizer production. You know, it's so interesting that sometimes we go to ESG summits and people say, oh, we should do business related to ESG. Well, fortunately, anything and everything we have been doing in the company has been related to ESG. When people are only talking about decarbonization and climate change, we have been actually producing millions of MMBTU per year of biomethane and treating millions of tons per year of waste. So just since 2010, our company has installed projects and plants across the world which kind of divert about 8 million tons a year of organic waste from landfills. That's like more than 6 times the waste produced by city of LA, Los Angeles of 20 million people. We produce 5 million MMBTU per year and about 134 megawatt of clean energy. So we understand this. This is our only business, and we kind of are walking and trying to move the needle forward on this. Global company, ordered in Canada, large base in the US. Europe is where our roots come from. We are quite active in sub-Saharan Africa, and Asia. From Singapore office, we cover the APAC region. 1,700 anaerobic digestion plants plus built in the last 30 plus years over 4 continents. So these are some of the facilities. I'll just skip this. Again, I'll skip that. So let's get into biomethanol production. So I'm going to talk about biomethanol or green methanol production from the route of organic waste to biogas and biogas to biomethane. Yeah. And then the second route is what Carlo and Michael just touched on, is when we convert biogas to biomethane, we get a byproduct, which is biogenic CO2. And that biogenic CO2, if you combine with hydrogen, you get e-methanol. So as a company, we focus on both biomethanol and e-methanol. For e-methanol, we would then partner with companies who build the hydrogen plants. So the 3 major feedstocks, which we believe could be, the right word in English could be perennial source of feedstock. As long as human beings are there, as long as urbanization is going to happen, there is going to be municipal solid waste, there's going to be food waste. So organic waste can give us biogas, and biogas to biomethane, and biomethane to biomethanol. At the same time, when you do biogas to biomethane, as I explained just now, you get biogenic CO2, which when combined with hydrogen makes e-methanol. The second biggest feedstock we focus on is agricultural waste. It's either rice straw, wheat straw, and manure, cow, dairy, chicken manure, so any kind of organic waste coming from agricultural and industrial practices. And the last but not the least is interesting, actually, to kind of create massive carbon sinks. We're also focusing on napier grass, and we have a lot of experience in doing that. So you can kind of have plantations of napier grass, perennial source, cut it, put it back into digester, nutrients goes back to the soil to grow the napier grass and stuff like that. So potential feedstocks, which we as a company are looking at globally and working on, quite a few of those are municipal solid waste, rice straw, the grasses, sludges from wastewater treatment plant. Every city has wastewater treatment. Every city who has wastewater treatment plant has organic sludge. You can make biogas out of it, and animal farm waste. The key parameters which we look for are, some countries have the right policy, the right feedstock aggregation, which is collection, logistics, and the economics of it, and the scale. The real question here is how to make this at scale. So these are the 2 pathways. If you see, what we are looking at is the first pathway, when you see here, is municipal solid waste, where we kind of pre-process the waste and then have anaerobic digestion to make biogas, biomethane, SMR to methanol. One of the byproducts what we have is RDF. Now I think Tim Enerkem is going to talk about how they convert RDF to methanol. What we do is that either we can make that and give it to people like Enerkem, or we then use this to make our own power, which is utilized for the production of methanol. So complete self-contained facility making its own. The second one is combining municipal solid waste, organic fraction, and agricultural waste to get massive economy of scale to make methanol. That's an interesting process which we have right now, where we go all the way. Imagine municipal solid waste coming from your home, my home, to sorting, screening, extracting organics from mixed waste. Yes, I repeat, we can extract organics from mixed waste. We have now 14 plants in the world running on it, where we get that feedstock and we put that into an aerobic digestion system, make biogas, SMR to methanol, and the RDF, as I just mentioned, can be then used in an RDF boiler to generate actually heat, steam, electricity, and CO2. This CO2, for example, can also then be blended with some hydrogen to co-locate basically a biogas to biomethanol, RDF to CO2, capture CO2, hydrogen, and make more methanol. So it's like a community of a complex which is biomethanol and e-methanol together to bring massive scale. So this is the secret sauce which the company has on extracting organics. In layman's term, we call it a garlic press, which kind of extracts organics from mixed waste. So now we have extracted organics from an MSW, and this can be, this is running. So none of the technologies which I have presented so far are lab scale or are coming from a laboratory. All the stuff which we are now looking at building have been built. So we have plants running and operating with these technologies, which is very interesting because when investors want to put a lot of money into biomethanol or e-methanol projects, the last thing they would want to take is a technology risk. And I think that's where, since we are also as a company investors, we understand that when you look at equity and debt providers, what are the boxes you got to tick? And that's where we use proven technologies. As I was just explaining, it's like mixed waste, you extract the organic fraction and the rejects, and this organic fraction then you polish further and put it into an anaerobic digestion process. Second thing, we touched upon it. I personally think, and I've done a lot of research on that myself, and we're looking at a lot of projects, and there are 2 or 3 large biorefineries of methanol which could be built just on this waste, which is burned every year. And we have proprietary process to convert rice straw into biogas at scale. I'm talking about just from the rice straw, looking at facilities of about 80,000 to 100,000 metric tons a year of biomethanol. The issues we are grappling and trying to manage are the strategy to collect at scale. We're talking about hundreds and thousands of hectares of rice plantation. Second is the logistics, and then also kind of trying to mix it with other feedstocks to do co-digestion. Again, here we are working with, of course, people who are from the farming community, large landowners, and the key here is aggregation, but also incentivizing the farmers that why they should give this waste of theirs to us. And then we are working in a very interesting fashion with giving them back seeds, fertilizer, and the logistics cost is being worked out. Imagine this much amount of feedstock. If it's going to come to a centralized facility, we're talking about 30-40 square kilometers. We are even thinking that since we make biogas, the trucks which are going to be used to transfer rice agricultural waste or wheat straw from the fields to the facility will be powered by bio-CNG. So you don't use diesel trucks anymore, you use CNG trucks, which you're anyway making from biogas. So it kind of make it complete life cycle as carbon negative, basically. This is a third thing which I mentioned. So again, doing a small recap, we talked about solid waste from cities and industries. Second was rice straw or agricultural waste. And the third thing is napier grass. I think there is a lot of low productive barren land which can really be converted into carbon sinks. And I'm talking about thousands of hectares of this in Southeast Asia, in Africa, for example, and even Latin America. Tropical places, humidity is very good, water requirement is not high, and then there are vast tracts of land which are not competing with crops, because that's a sensitive topic. The last thing we want is to convert crops, maize and corn, into napier grass for fuel. But I think there is enough land, and from our experience, we have done a lot of, again, on the ground work. There's a lot of land available, and again here we are using Anaergia proprietary technologies to really reduce down the cost of processing at scale. That's the key, at scale and lower cost, so that we achieve the biomethane requirement. Again, consolidation of land is a big problem here, because you're talking about a huge amount of land. And the economics is the cost of growing, cultivating, cutting, and bringing it to the plant, and the logistics around it. Anaerobic digestion is something which has been running in the world for maybe 150, 200 years at scale. Huge plants. Our largest plant is in North America, which is generating about 1.2 million MMBTU per year of green gas, which is kind of equivalent to about, if it was to convert to methanol, we're talking about 50,000 metric tons a year of methanol already, for example. Our largest project is under construction in Denmark, and that, if I convert into methanol production capacity, it can be 70,000 metric tons a year. Again, this is something which I wanted to say because I'm not going to say how e-methanol is made. Michael and Carlo has covered it, but we are very proud, and it's an honor to kind of be supporting one of the world leaders, which is Merck's, to fuel their first container vessel on e-methanol. So this is a project which is being built by European Energy in Denmark, and we are supplying biogenic CO2 from our biogas plant to their facility, which is going to be combined with hydrogen. This is the first large e-methanol at scale production facility in the world. And really, it's an amazing thing that things are moving in this space, and people are not just talking about it, but things are happening. And this is the facility from where we are going to give biogenic CO2 to European Energy. As I mentioned, the first phase of the project is completed. The second phase is going on. We're talking about 60,000 tons a year of liquefied biogenic CO2. In this project, we convert different kinds of organic waste into biogas and biogas to biomethane. You get CO2 as a byproduct. And we have a 10-year offtake contract on this project. This was the facility I was talking about, where this is in Los Angeles, the largest organic processing facility in North America. And if you see this kind of biomethane, we're talking about easily large quantity of methanol which can be generated. In this particular case, we make biomethane because the regulations around biomethane in California and the federal RIN standards in the US are very progressive to make methane rather than methanol. You get more money when you make methane than methanol, and that's how it is structured right now. That's, of course, another project which is, just to give you an example that how wastewater sludge, every city has wastewater or generates wastewater, and we are converting wastewater sludge of a city combined with food waste of the city and converting that into biogas and green energy. Sorry for that long story, but I would like to summarize with key action and takeaways. So we all understand that maritime decarbonization needs to happen like yesterday morning. In our experience, humble experience, I think waste to fuel is doable and possible. I again underline and underscore at scale. Technology is available and proven. People like us are willing to give performance guarantees and process guarantees. Feedstock aggregation and regulatory support is needed, especially in developing economies where maximum methanol consumption, for example, Singapore and the regions of Suez Canal and Panama Canal where ships pass. Critical points for commercial viability, Tim, is the feedstock cost, which would then determine the cost of methanol. Location is very critical. It's one thing on making methanol, and it's another to bunker it, store it, and be able to give it to the ships. So there is a lot of cost involved in that particular infrastructure, which we all need to then calculate and put it into per metric ton. I think scale is important. You've got to build large scale plants to be making methanol. I mean, we just saw the numbers, Tim, in your slide. What we are touching is like just the surface, or even not scratching the surface. Carbon offset price could be interesting. We are seeing a lot of people working towards that. Mitigation of risk is towards feedstock is to do co-digestion, having more than one type of feedstock. And the beauty with biogas is that it can kind of digest more than one feedstock, organic. Last but not the least on this call, if you see, partnership is key. So partnership between technology providers, Michael, developers like you, investors, consultants, government agencies, and so on and so forth, for all of us to come together and build these plans. With this, I end my presentation, Tim. Thank you.
Thanks, Kunal. I'm a little wary of the time, but Kunal, I do have like a question for you, and it might be a tall order, but like if you could summarize in one key takeaway, or maybe let me set the context first. I think like with the production of biomethanol and feedstock acquisition and the kind of feedstocks that you have already covered, logistics is always the key thing. It determines a huge part of the cost of production for biomethanol, and also the subsequent landing cost of a fuel, for example, if you're supplied to the maritime industry. From Anaergia's perspective, what is one key takeaway, a solution that you guys have deployed regularly, and it has shown tremendous results in the streamlining of the logistics of acquiring feedstock?
I think, Tim, very good question, and I think the answer would be that it will be different from country to country and region to region. Just take an example of municipal solid waste. Clearly, in developing nations, for example, in Australia or in Europe, we get paid for processing waste, right? So then it's no more a cost. We get paid when the waste comes to our facility. So that's a beautiful angle. Of course, the cost of processing waste is also quite high. So capex of these facilities is higher. When it comes to agricultural waste, so far the experience is to work with local lay of the land people who have to be bought in as a win-win. If they see that this is just somebody coming in and is going to make methanol and going to make a lot of money out of their land, I think it's going to be a problem ultimately in a long-term play. So I think what we try to always do is that to get the local cooperative society or some landowners to come in at some way or the other as part of the project life cycle and be involved in the project from day one, that it's their project. We have seen in a few facilities which we are developing there, the government has stepped in to make them a really proud thing that it's green fuel is coming to their plant. So the government is also stepping in. Land is always a local issue. So in terms of agricultural waste and epigrass, land mass owners have to be bought in. You can have one anchor and then people around it. Second thing is, I think logistics is pretty much, in my view, relatively easier to manage. You can even, as part of the project company, SPV, you can even have your own logistics setup, which we are looking at in a few projects. So standardizing that and professionalizing that, and that's why projects like these are not easy. It needs more than just a banker giving a check or a technology provider saying I have the best technology. It goes beyond that. It's socio-political, it's economical, it's politics, it's local lay of the land. So I think everything has to come together. So sorry, Tim, for a roundabout answer, but no secret formula there. But yeah, every place is different.
Thanks, Kunal. No, I realized that it might be a little challenging to answer that question given the time constraints that we do have, but we'll get back to you during the Q&A. What I'll do right now, guys, is that because David Jung is not online with us today, I'm just going to broadcast the presentation that he recorded for this session. If you have any questions for him, do feel free to direct them to him through me, but we'll take it offline after this call. So, okay, with that, let's see if I can do this.
Hello, everyone. My name is David Zheng. I've been with Enerkem for over 8 years now, and I'm leading the business development activities for the Asia-Pacific region. I started as a process control engineer at the Enerkem Alberta Biofuels facility, and I moved into business development role in 2019. Sorry I'm not able to attend this webinar in real time, but I hope you will find my recorded presentation informative and useful. If you have questions and/or comments, please reach out by email. Enerkem is a technology and a project developer that offers waste management, decarbonization, and a sustainability solution. Enerkem is the first company in the world to produce bio and renewable methanol and ethanol from non-recyclable, non-compostable waste at a commercial scale. Our solution replaces the use of fossil feedstocks like petroleum and natural gas to produce sustainable transportation fuels and circular chemicals that are used in a broad range of everyday products. Our innovative technology enables sustainable solutions for waste management, energy diversification, and the implementation of a circular economy. Our technology is easily scalable and it has been carefully vetted by our world-class strategic partners such as Shell, Suncor, Proman, Repsol, and Suez. Enerkem's technology is a prime example of how the carbon in waste can have a second life by being recycled into new products, diversifying the energy mix, and making everyday products greener whilst offering a smart, sustainable alternative to landfilling and incineration. In our four-stage Enerkem process, first, we refine the waste to feedstock by reducing the inert content to 16%, shredding the waste into small pieces less than 70 millimeter, and then drying the waste to about 10% moisture. Second, we gasify the feedstock to raw syngas. Third, we purify the raw syngas to ultra-clean syngas ready for catalytic conversion and condition the syngas molecule ratio for optimum downstream conversion. And fourth, We convert that syngas to advanced biofuels and circular chemicals. Enerkem's technology can process a very wide range of feedstocks. So far, we have successfully tested over 25 feedstocks in our process. Most common feedstocks include municipal solid waste, agricultural biomass, forest biomass, as well as treated wood and C&D wood, and waste plastics. Feedstock site selection is an important consideration when developing a project. Feedstock is selected considering availability, cost or tipping fee, and its impact on production yield, product carbon intensity, eligible incentives, and ultimately the realized project financial performance. Thus, we have developed a tool to optimize feedstock selection based on local waste basket and project profitability. On the left-hand side of this slide, it shows that Enerkem focuses on valorizing residue MSW, biomass, and waste streams rich in plastics, which are the reject fractions from the mechanical recycling facility. This has positioned Enerkem at a higher level in the waste management hierarchy above the conventional incineration practice. On the right-hand side, it explains in general terms how feedstock characteristics affect the process and project economy. In short, for biomethanol production, the ideal feedstock would have high carbon content or calorific value, low inert and moisture content, relatively high density, and high biogenicity. As you can imagine, biogenic content is important for biofuels. For MSW, the biogenic content typically ranges from 50 to 65%, with the rest being fossil-based content. Enerkem's technology has been fully proven at industrial scale. Our first of its kind commercial demonstration plant, Enerkem Alberta Biofuels, is located inside Edmonton Integrated Waste Management Center. This facility complements a range of recycling and composting processes by recovering unrecycled reject fractions from these other facilities. This integrated waste management center treats both municipal and commercial waste coming from the greater Edmonton area, which has a population of about 1 million. Since 2019, this facility has been processing 3 types of feedstocks, which are waste wood, post-recycled municipal solid waste, and waste plastics. We have accumulated abundant experiences and learnings and incorporated this into our second-generation technology and process. Every year, this facility can receive up to 200,000 metric tons of unrecycled waste and convert these into biofuels and circular chemicals. In 2016, the facility obtained a certification from the International Sustainability and Carbon Certification System, or ISCC, qualifying our methanol to be sold as biofuel in Europe and in UK. In 2017, the facility received the lowest carbon intensity value for its ethanol ever issued by the British Columbia Ministry of Energy and Mines under the Renewable and the Low Carbon Fuel Requirements Regulation. It is also the first ever waste-to-biofuel facility to be approved under the U.S. Renewable Fuel Standard from the U.S. Environmental Protection Agency, EPA, in 2017. Other than our plant in Edmonton, we have a very healthy project pipeline, some of which we can disclose are shown on this slide. A full-scale commercial facility in Varennes, Quebec, Canada, is currently under construction, and commissioning is scheduled for 2024. The project partners include Shell, Suncor, and Proman. Enerkem's technology will also be used to build the first waste-to-chemicals plant on the Iberian Peninsula in Amolel, Tarragona, Spain, in collaboration with Repsol and Agbar. Finally, based on substantial targets and demand for sustainable aviation fuel, Shell, along with Enerkem and the Port of Rotterdam, are looking to build a waste-to-jet plant in Rotterdam, the Netherlands. We're also developing projects in other parts of the world. The Varennes carbon recycling plant is using both MSW and residual biomass as feedstock, and it can convert roughly 200,000 tons of these non-recyclable waste to about 125 million liters of IMPCA spec methanol per year. This is a one gasifier train system with green hydrogen import. With this green hydrogen produced from water electrolysis by green electricity, the methanol produced will have a greenhouse gas reduction of more than 80% versus regular fuel. This project is in partnership with Shell, Suncor, Proman, and support from the local government. The Tarragona project is a two-train Enerkem system with hydrogen import, which can convert roughly 360,000 tons of non-recyclable waste to about 270 million liters of IMPCA spec methanol per year. The biomethanol portion will be sold as biofuel, and the rest will be sold as circular methanol. The GHG emission will achieve over 65% reduction compared to incumbent technologies. The project has been selected by the European Innovation Fund as one of only 7 projects of 350 applicants for 100 million euro support. This project is done in collaboration with Repsol and Agbar. The Rotterdam Waste-to-Jet project has the same waste processing capacity of the Tarragona project, but with a different focus on sustainable aviation fuel production, with roughly 70% GHG reduction comparing to incumbent technologies. This project is done in collaboration with Shell and the Port of Rotterdam. Thank you for your interest in Enerkem. If you have any questions, please feel free to contact me, and I will get back to you as soon as I can.
Okay, so we are back. Let me just transition to our next slide. Okay, so now we'll move into the Q&A session. I do apologize. It seems like we are a little behind time. So I'll remind the speakers, if possible, and when possible, try to keep your responses succinct and brief. So without any delay, I'll issue the first question to Carlo. Carlo, this is a question that I thought was of particular interest from the audience. This individual has asked if we divert municipal solid waste from incineration or landfilling, would that make methanol greenhouse gas or carbon negative?
Methane from a landfill, right? And then turn it into methanol.
So not methane, but if we prevent municipal solid waste from even reaching the landfill, so it goes straight to a biomethanol production facility. In that process, we avoid emissions from landfills. Would that would that process be considered carbon negative?
From an LCA perspective, I would think so, because you would avoid, if you can prove that you would avoid a landfill in an alternative situation, then that would of course have a huge benefit. You would avoid those methane emissions. I'm not sure. I don't think this will be recognized in the legislation in Europe.
All right. Thanks. Thanks, Carlo. I will move on now to the second question that was brought up, and this is for Michael. So Michael, the question goes as such: does the form of carbon for e-methanol production have to be CO2? Can it be perhaps another source of carbon such as char? Do you have any thoughts on that?
No, it doesn't have to be CO2. I mean, of course, there are all sorts of carbon you could start with, but ultimately, in order to make the methanol using your conventional synthesis reactor, you're going to have to generate a syngas of some
CO2.
sort. And CO2 could form part of that, but also if you can get some carbon monoxide, you end up using less hydrogen, per unit of methanol. So, and the other thing to remember too is scale. It's very challenging to make methanol or anything from syngas at relatively small scale. You can certainly, if you can increase scale, you can reduce your unit cost typically quite substantially. So they're the two that determine, what your ultimate feedstocks are. You're trying to increase scale as there's always some constraints, so that you find your feedstocks, in the case of bio or e-methanol, your feedstocks will ultimately be your constraining factor. And it may be a carbon, but it also might be your renewable energy that's your constraining factor. That certainly is one of the issues we have in Tasmania. We have to bring out a new power plant with us, and you can only build wind farms in particular a certain scale easily. So yes, I don't know if I've answered the question there, Tim, but you do have to get it to syngas to do the your conventional methanol synthesis.
Thanks, Michael. Moving on, Kunal, this is a question, I think it's a rather long one, so I'm going to try to condense it, because the question pertains to different types of feedstock and the process efficiency of converting them into biomethanol. But I'll just pick two categories that I think are representative of the list, and they're also pretty different. But the question goes as such: how many tons of rice straw or sludge do we need in order to produce 1 ton of green methanol? Is that something that Anaergia has looked at so far? Or if you don't have those numbers off the top of your head, I think it's something that we can also go back to this individual with an answer at some point.
Absolutely. So Tim, I think I don't have that exact number, but what I can tell you is that recently from the head, about 1,000 tons of organic waste or food waste could actually produce about 35,000 metric tons per year of methanol. So that's food waste, and for sludge you will need a bit more higher number, and on rice straw will be a bit more in the same level as sludge. So yeah, 1,000 tons a day of food waste would generate about 35 to 40,000 metric tons a year of green methanol, biomethanol.
Thanks, Kunal. So now we come back to Carlo. Carlo, I think this might be an interesting one. It was said that you mentioned that CO2 reabsorption from biomass is a short cycle, and from an LCA perspective, do you differentiate between different types of biomass to assess the duration of the CO2 reabsorption cycle? I'm not sure if that's
Yeah, I understand the question. So some biomass will take longer to grow than other biomass, and so there is a there is a concept that is called carbon depth, which tries to take this into account. That if you would, for example, use a full-grown tree and you use it in your renewable fuels, it would take maybe 80 or 100 years to grow back. It's very important to look at this from a landscape perspective. And also, I think nobody wants to process whole trees, as Michael also explained. It's forest residues that come from other industries, so it's unavoidable biomass in many cases. And if you look at it from a landscape perspective, it's a bit more complex, but I think it's in general it will still turn out to be carbon neutral as long as the forest is sustainably managed.
Thanks, Carlo. We have one more question for Michael, and the question is: it seems like in Tasmania and the particular region that you have identified for the ABEL Energy project. The circumstances were very ideal. There was easy access or close. It was close. There was close proximity to the timber industry, but also there was a fully renewable grid. In your process of investigating other regions, or if you have taken it, or if you have conducted any kind of research on other regions, have you seen any other localities that enjoy similar ideal circumstances within Australia or outside?
Yes, we have. It's interesting. Certainly in Australia, the forestry industry has often developed around ports. So you're often starting with a port which has a forestry industry nearby, and that's just been a historical thing, so that you can move wood chips or logs by water, which is always much cheaper than by land. And so that's a good starting point, and I think you'll see that not just in Australia but also in many other parts of the world. The bit that's new is the renewable power generation, and what you're seeing now is an emerging industry generating new renewable power solutions. Now, not just for the methanol industry, this is also for data centers, for example. Data centers need a similar volume of electricity that, say, a methanol plant needs. So you're starting to see combinations of wind, solar, batteries, and so forth to try and provide as higher capacity of renewable power to a whole range of industries, and certainly the methanol industry can take advantage of that. So just to summarize, you've often already got a timber industry that is centered around a port, certainly in Australia, you see that quite often. And now the emerging renewable power generation solutions are giving you that third piece that you typically need to make your lowest cost green methanol.
Thanks, Michael. So due to time constraints, I'll have one more, and this will be the final question for Kunal. The question here is, lignocellulosic feedstock requires enzymatic pretreatment to produce biogas, and it's expensive. How does Anaergia overcome this increase in cost?
Again, in my slide, I mentioned that we have a proprietary process, and good news is that we do not depend a lot on enzymatic process. So the question is correct from the person that enzymatic processes are expensive. So we've decided not to have our processes based on that. And the idea, as I said, when we start developing this project from not just a technology perspective, but also as a developer, and the ultimate goal is to make methanol at the cheapest cost possible. And in order to do that, then we do a backward integration, and we see that whatever works best is going to be used. And then there is always this efficiency that, okay, you put in $10 million of more capex, you get 5% more efficiency, but that also gets OPEX. So we say that we're ready to sacrifice that 5% more efficiency and make the process more bigger and robust. So it's a techno-economical feasibility which we play.
Thanks, Kunal. Okay, so with that, I would like to thank my presenters for taking the time, but also the audience for staying with us. I do realize that we have ran over the allocated time, but if you do have any extra questions for our presenters, do feel free to direct your questions through me. I'll convey them to the presenters. We can take some of these interactions offline. But also do note that there are handouts that you can download from the control panel on your screen, and they will have the slides for today's session, with the exception of Anaergia slides. So if you do have any questions, or you want to refer to some of the slides that they have used for today's session, do feel free to reach out to Kunal or me, and we'll be happy to entertain some of your queries. With that, thank you guys, everybody, for today's session, and have a good day.
Thank you, Jay.